We now have started recording, so please turn off your mics and your videos to avoid any distractions for Merlinda, and also feel free to write any questions you have in the chat box. So now we're recording. Please, Merlinda, you can start.
Thank you very much. Just a moment, so I'll share my screen. All right. So good morning from me as well. Thank you so much for this kind invitation. I really appreciate having this opportunity to talk to you today, and special thanks to Natalia for hosting and organizing this webinar. So as Natalia said, my name is Merlinda. I am currently working as a postdoctoral RA at the University of Glasgow. And today I'm going to talk a little bit about the issue of renewable curtailment and how this might affect capacity investments. And I'll also discuss, we'll discuss about needs for developing tools that can model strategic interactions of different actors that are emerging in the deregulated, if I may say, energy landscape. The work I'm going to present today is related to my PhD work undertaken at the time at Heriot-Watt University. And this work was funded by CESI, the Center for Energy Systems Integration, and which is a project funded, of course, by EPSRC. So before I kind of get on with my talk, let me provide an overview of today's presentation. So in a nutshell, this work explores game theoretic modeling to study line access and curtailment rules and their effect on new capacity investment decisions that are taken by self-interested and private investors. Now, these capacity investment decisions may refer to renewable generation capacity, grid expansion or grid infrastructure, or building new storage capacity. More specifically, we focus on privately led initiatives for grid reinforcement, where we have a private investor that develops the grid infrastructure and then shares access to the grid with other competitive investors, such as renewable generators or energy storage providers. And of course, charges them for the use of the line. We developed a model that optimizes the capacities that are being built and captures these strategic interactions between different and competing investors. Now, before jumping into the technical part of the paper, just a little bit, a few words basically about the main motivation behind this work. So the and the context and the background about this work. So the energy landscape is currently going through a massive transformation, and this, of course, is led by the adoption of renewables. In fact, renewables are kind of the fundamental technologies or a block for all climate change policies that are implemented globally, including the EU and the UK. At a EU level, you can see here some of the EU targets. Some of them are being debated if we could actually achieve more. Regarding the UK became the first G7 country with a net zero emissions targets for 2050. Now, such policy targets and financial incentives for private investors have led to a massive development of renewables. In 2020, for example, the global renewable market was estimated to be more than $880 billion. This is projected to reach almost 2,000 billions by 2030. Now, such levels of adoption have transformed electricity grids, which are becoming more decentralized and complex to operate, as now energy is being supplied by the like of PVs and wind generators, which are typically located closer to the demand and are often connected to the medium voltage or low voltage level. And this is challenging the way that power systems are traditionally managed and operated. Now, with every challenge, though, there are opportunities arising, leading to the adoption of smart grid, digital technologies. Some kind of key concepts that are being discussed around the topic of smart grids are, you can see them here in red. And key elements as well are artificial intelligence, AI techniques, and game theory techniques, which have an increasingly important role to play in this emergent energy landscape. Now, the research work of this presentation developed a game theoretic and an agent-based systems framework for modeling strategic behavior of investors in this landscape. Now, due to the variability and dependence on weather patterns, the integration of renewables is not seamless and comes with its own challenges. One significant challenge is the increasing renewable curtailment observed in energy systems. Now, curtailment is when energy that could have been produced by renewables is being wasted in order to guarantee the safe operation of the power system. In other words, renewable production cannot be absorbed due to grid or network constraints. These are related to technical limitations, for example, related to frequency, voltage, and so on. And also violating thermal limits of cables and so on. Now, why curtailment happens? There are two key or primary reasons about curtailment. Either because there is excessive renewable capacity installed at a certain location, or because the network infrastructure is not enough to cope with all the renewables that are being deployed. Now, this issue of curtailment, as we increase, of course, the penetration of renewables and we adopt more renewable technologies, is becoming more critical. And this is shown kind of by the rising costs that we have observed and the wasted renewable energy that we have observed in several countries, including, for example, Germany and the UK. Now, a side note here is that usually when wind turbines, for example, are curtailed, they are paid for, okay? They get some form of payment. And you can see here some older figures, but still relevant to show the extent of the problem. You can see here costs that are related to the UK. We can see that up to 32% of onshore wind was curtailed in 2016, for example, in Scotland. Now, as we know, kind of much of Britain's onshore wind is in the central belt of Scotland and north in the UK. And there is often congestion on the lines that try to carry this down to the demand centers, which are typically larger in England and Wales. In Germany, the cost for curtailment was about €500 million only in 2015. And there was a 27 times increase of wind curtailment between the years 2020 and 2016. If we look at more recent figures, you can see this, hopefully you can see this, okay, these two images here. These were published by Imperial College London. So we can see here on the left the annual curtailment of wind energy and how it evolved in the last decade. Okay, and on the right we can see the cost for this curtailment. So what we can see here is that in 2020, curtailed energy surpassed 3.8 terawatt hours in the UK. Just to give you some more numbers, sorry for being here with the statistics a little bit too analytical maybe, but over that year, so over 2020, wind farms supplied 69 terawatt hours of electricity, okay? But this could have been much more because 3.8 essentially were wasted, was curtailed. This is 6% of the available wind output that we could have had. And just to give a little bit more context as well, 3.8 terawatt hours of electricity would be enough to power every home in Wales. Okay, so it's not it's very important. It's not a low amount. Also, the cost for this curtailment, the cost that the national grid had to pay, it was 282 million pounds. So that would be about around £10 per household in the UK. And if we look at the right picture, we try to see at curtailment costs in another way. So this picture shows how much does curtailment add to the cost, to the wind cost of generation. We can see that in 2020, curtailment added £4 to each megawatt hour of wind energy being generated. Now, one kind of long-term solution to dealing with curtailment is actually reinforcing the grid. However, vast amounts of money are required to achieve such reinforcements. And again, just to give you some figures here, 200 billion euro are required for capacity investments. This includes grid infrastructure in the EU. And if we look at the United States, we can see that there is an estimate of $2 trillion only for grid upgrades, okay? So the second figure is only for network expansion that would be required in the US by 2030. Now, such investments usually are publicly funded. However, from a public policy standpoint, it would be useful if we could attract private funding, or if we could achieve some degree of private development of network upgrades and expansion. In fact, it could be possible for operators to grant a license to a private investor to build a line under the condition that this line will also grant access to other generators, possibly competitors, who are charged though for using this infrastructure. Now, a significant kind of example or case that kind of led to this idea relates to the area of Kintyre in Western Scotland. Now, this area is, it has a great potential of wind, but also tidal energy. What happened though is that the grid, of course, it was designed years ago. Therefore, the grid was built having in mind the purpose of just serving a typical rural area, okay? And that meant that when this area was faced with this huge investment interest, then we required significant grid reinforcement to happen in this area, okay? And this is not unusual. Quite often great areas for the development of renewables are remote and away from large cities or demand centers. And therefore grid capacity is not sufficient, and we need to to invest in order to integrate these areas and renewables being built there. Now, what also happened in the Kintyre is that usually renewable developers, they join and they pay for their own kind of connection line, if I may say. And of course, they have to endure significant time delays and so on. So this also has sparked a debate on how we could maybe transform, or we could offer alternative ways or explore alternative models and structures that maybe allow shared grid access. So for example, instead of having several renewable projects building their own kind of capacity line, a solution could be that for the first kind of project to build a larger capacity line, and then granting also access to other projects in the area. Now, just to conclude with this specific example, this vast interest that I said existed for this area from renewable investors actually led to a significant project and a subsea cable being built. This costed 230 million pounds, but crucially allowed for 150 megawatt of additional renewable capacity to be installed in the Kintyre. Now, the issues that this area was kind of dealing with formed the initial motivation of this work. And we did keep this as a case study where we kind of showcased the practical application of the theoretical models that we developed. Now, to investigate this idea of shared grid access, we started with a very simple model. So this is the kind of our initial approach to this issue. And this model has two locations. Location A, which represents a model of high demand, that could be a mainland position, for example. And location B, which represented a location that has some local demand. But crucially, the important thing here is that it has very high renewable potential. We also assumed two players. So player one builds some renewable generation capacity at location B, and also builds the transmission line from A to B. Now we will call this player short the line investor, despite the fact that he's also building renewable capacity, but just to distinguish him from the other player. And player two represents all other renewable investors that are located at location B. Okay. And the idea here is that we have a shared access principle. That means that the line investor will build the transmission line, but he also has to grant access to these local generators, okay, who have to pay some transmission fee, of course. And now the key question here becomes, what are the optimal generation capacities that the players should build in order to maximize their profits? Okay, this is the question. And we can see that this curtailment, this shared access principle can lead to this to a complex strategic interplay between these two different players. And we model this as a Stackelberg game, or a leader-follower game, where the line investor is the leader, as he has the first mover advantage, and he is the only one who can build the line. And local generators are the followers who can observe, obviously, the line being built and can use this and can connect to the and can get access to the demand in mainland by using this line. Now, this question of what are the optimal generation capacities at this Stackelberg game can be answered when we solve the game, okay? And this is when we can find the equilibrium of the Stackelberg game. The method for finding the equilibrium is that of backward induction. Now, bear with me, I will explain this with a more complex and finalized model that I will show later, so I won't go through it. But basically, the steps are that you can compute the agent, the two players' profits, okay? And then the leader needs to find, for every possible strategy of the leader, what are the followers' best response? What is the follower's best response? Okay. So for every strategy, we get a best response. And then from this set of best responses, the leader will actually choose that capacity, that strategy that maximizes his own profit. Okay. Now, if we assume in a very simplistic initial model that we can estimate capacity, generation and curtailment and so on, these are required to, of course, to estimate the profits of the players. So if we assume that we could rely on expected values or on kind of long-term averages, and if we follow these simplifying assumptions, there is we are able to find the closed form solution of this game. Okay, so we can solve this game analytically, and this is useful to do an initial examination of the equilibrium properties and so on. But if we want to look at a more realistic model, then we have to take into account the fact that wind generation is actually stochastic and demand varies constantly. Also expected generation, you can see some of the expressions here. The expected generation shown at the first equation, and the other one is expected curtailment. So we can see that these are actually functions of the player strategies, and some of these are also interdependent. And therefore, we are not able to solve this game analytically anymore. Okay, and but it is possible to follow a data-driven approach and to solve this game, as I said, by a data-driven approach. Now, again, bear with me here. I will skip this part because I'm going to explain a more complex model, and I'm going to stay there to show how this data-driven approach can actually happen. But in case you are interested, there is this paper here that I'm showing that discusses this particular model. Now, on the more complex model, what do we have here? So we have the same two locations, okay, the mainland, of course, and the location where renewable generators can be placed, the great location for renewables, location B. And now we assume 3 players because we also wanted to add storage in the mix. So we have player 1, or the line investor, who now is the leader, of course. And the line investor builds the transmission capacity from A to B and some renewable capacity at location B. We have, as before, player 2 representing all local generators or followers in this area. And we also now introduce a new player, which is the storage player, who is able to buy energy from renewables that would otherwise have been curtailed. Okay, so we do place some local storage here at location B. And the key research question here, again, is what are the optimal generation, transmission, and storage capacities that maximize the agent's profits, okay? And we can see that this leads to a more complex game formulation. This can lead to a Stackelberg-Cournot game or a leader multi-follower game, with the leader, of course, being the line investor who builds the line, and the followers being the local generators and the storage player. Moreover, we want to look at what are the strategical interactions between these three independent but self-driven and self-driven agents. And these type of questions can be answered by when we solve the Stackelberg-Cournot game. Just as a recap, what do we need how do we analyze this game? Is that we look at what are the player strategies. So the strategies are also called the action set. So what are the actions or the strategies that each player can take? So for the line investor, it is building the renewable capacity at location B and transmission, of course, the line capacity. For local generators is how much renewable capacity to build, and for storage, how much storage capacity to build. Now, the optimal capacities will happen at the equilibrium of the game. However, finding this equilibrium is not an easy task. One, the action sets, so the strategy space of the agents are large, okay, the strategy spaces for the agents are large, they are continuous, and even there can be multidimensional, such as in the case of the line investor who has two actions, the renewable generation capacity and the line capacity. Now, this makes the payoff calculation or the profit calculation a difficult task. Especially as energy that is being produced, because we have to estimate energy quantities in order to estimate profits. But the energy quantities then depend on the collective decisions and the interaction of agents. Moreover, when we introduce storage, we introduce also time interdependencies, and also the operation of a realistic and energy system dictates complex rules, such as to which asset takes the priority of dispatch when demand is being served, and so on. So for all these reasons, an analytical closed form solution of the game cannot be achieved. And instead of assuming simplified, smooth mathematical functions and so on, we proposed an algorithmic approach that relies on payoff enumeration that is taken directly from data-driven simulation analysis and more realistic assumptions about energy system control algorithms. Now, this solution can be summarized in the following steps. So first of all, we decide on a feasible strategy space for all agents. For example, we discretized the agent's action set instead of keeping it continuous. And this is not, it's a good assumption in the sense that in the real world, investment decisions may be restricted. So actually we solved a reduced game, if I may say, but note here that even in the reduced game, there are hundreds of millions of strategy combinations that need to be considered in order to find the equilibrium of the game. At the second step, energy quantities such as production, curtailment, and so on are estimated based on a data-driven approach and control scheme. And this allows us to estimate the profits for each player, okay? From the profits, we can build what is called the payoff matrix, which I'll show in a minute. And finally, we can estimate then the Stackelberg-Cournot equilibrium, game equilibrium, by the process of backward induction. Okay. Now, how do we achieve backward induction? We need to estimate energy quantities, okay, as a function of the player strategies. And we need to inform this by control of the energy system. So what we do is that for all possible strategies, we can estimate the power and the energy quantities. And you can see here on the right, some of the control kind of logic that lies behind it. So for example, when there is an oversupply of renewable generation, okay, what we do is that we first satisfy the local demand, okay? So we give priority to the local demand at location D. Then we satisfy remote demand, that is the demand at mainland. If there is more, then we store this in the storage system. And if the storage system is full, then we have to curtail it, okay? We have to curtail this energy. In the case of shortfall, this is on the left, okay, in this flow chart. Then we can serve this by storage, and we can satisfy, again, we first satisfy local demand, then remote demand, and of course, if there is any deficit, then this has to be taken by other sources from the main grid. Now, once we have these energy quantities defined, then we can plug this into the profit functions, okay? Apologies for all the notation and everything. The energy quantities essentially and associated costs and tariffs here are plugged into the profits, and this is how we can if we look at this payoff matrix that I show here, now you can see that this is a 3D kind of matrix, okay? In the x-axis, we have the storage strategy space, that is all equilibrium. Now, this was kind of the optimization process, or the finding of equilibrium process. So what we did next is that we wanted to explore what are the dynamics for the equilibrium, so how and the equilibrium properties. So we had to look at what happens to the equilibrium as we change different cost parameters. So that would be, for example, generation costs. That is, what happens if for different generation costs, renewable generation cost, either from the line investor or the local generators. Also, what happens? What is the dependence on the cost of storage, which is shown in scenario 5 here. Also, another thing is what happens to the equilibrium as we play with different tariffs, either for transmission or for storage. So how much does storage pay when it buys electricity from renewables? And the level of this payment, how does this affect the equilibrium? We also wanted to look at the energy system. So adding storage, what do we gain by it? How do things evolve, basically? And we look at several kind of key variables, and we compute this for every scenario. And we do these parametric studies based on the Kintyre-Hunterston project that I talked at the beginning, and we follow this data-driven analysis. So for the sake of time, I only show here two scenarios, okay? So here you can see, for example, the profits at the left graph. You can see how the profits evolve as we increase the transmission fee, okay? So as we increase the transmission fee, what happens to the capacities of the renewables, the transmission and storage capacity that is being built? On the right, you can see again what happens to the capacities being built, the optimal capacities being built at equilibrium as we increase the storage fee. So how much money storage is paying when buying energy from renewables. And we can see here, for example, what we can achieve by these explorative scenarios is that we can see how much we can increase, for example, the storage fee, and what would be the profitable capacity in this case. We also looked at, as I said, the kind of value added by storage, okay? So we compared the system with and without storage. Of course, note here, if there is no storage, then the game reduces into becoming a pure Stackelberg game, not a Stackelberg-Cournot game, like the initial model that we discussed, okay? So what we saw here is that when we introduce storage, what happens that, and looking at the profits here, we can see that the line investor is better off with storage, while the local generators are slightly worse off, okay, when storage is introduced. Moreover, we could see that we can reduce, of course, the demand that is served by the main grid, so by main grid imports, okay? This indicates that renewable integration can be accelerated when combined with storage systems. And finally, we looked at the curtailment figures and found that curtailment can be reduced with storage. We found a maximum of 7%. Despite the fact that there is storage also causes an increase in total renewable capacity being installed, okay? Because now renewables can also sell some of their curtailed energy to storage, so that led to an increased capacity being installed by renewables. Now, if you find this work interesting, there are two papers related to this work. One AMA's paper, that is a agent and AI conference, and an IEEE access paper where you could look this work in more detail. Now, just to kind of sum up, in this presentation, we looked at, we developed a game theoretic framework that models strategic interactions between private investors who can take investment decisions themselves on building additional capacity. And this method this analysis can be a decision support tool for investors and explores alternative models for this shared grid access principle. So some alternative access to grid infrastructure. The model also allows to see what could be suitable charges for transmission, but also storage, so that investments are profitable and investors can also participate in the game. And finally, a significant kind of contribution of this work is this approach of the empirical and data-driven approach for finding this complex equilibrium estimation, as opposed to kind of classical game theoretic approaches that use mathematical functions and mathematical analysis and for equilibrium estimation and find this analytically. Here are a few references. I can share, of course, the presentation with Natalia, and she can also share it with you. So this concludes my talk today. Hopefully that wasn't too much. Thank you all for listening. I'll stop sharing and I'll pass on to you, Natalia. Thank you.
Okay, great. Thank you very much, Merlinda, for this lovely presentation. I will now stop recording.